Good afternoon. Dear guests, professor, students, and friends of science. It's my great pleasure to welcome you all for today's lecture, organized as a part of our interdisciplinary scientific seminar series, an initiative created to bring outstanding minds and inspiring ideas closer not only to the academic community, but also to the wider public. There are moments in the life of a university that become more memorable than others. Today is certainly one of them. It's a great honor for us to welcome a scientist whose discoveries have profoundly changed our understanding of the universe, Nobel Prize Laureate in Physics, Professor Takaaki Kajita. For decades, Professor Takaaki Kajita has devoted his scientific career to studying one of the most elusive and mysterious particles in the universe, neutrinos. His groundbreaking research on neutrino oscillations provided decisive evidence that neutrinos possess mass. This discovery has fundamentally reshaped modern particle physics and open an entirely new chapter in our understanding of the cosmos, the achievement that was recognized with the Nobel Prize in Physics in 2015. Today's meeting is especially meaningful because it takes place here at Wrocław University of Science and Technology, a university that for generations has connected science, technology, and bold thinking about the future. We are also delighted that this lecture is open to everyone, because world-class science should inspire not only academic community, but all the people who looked at the sky and wonder how the universe truly works. Dear guests, please join me in giving a warm welcome to Professor Takaaki Kajita. Thank you.
Good afternoon. First of all, thank you very much for the kind introduction. Also, well, first of all, thank you very much for the kind invitation. Well, it's an honor for me to speak to so many people today. And today, I want to talk about exploring the universe from underground. Well, okay. In fact, I realized this title is too big to me. Therefore, I decided to add, mainly based on my research experiences. Well, okay, anyway, so today I want to talk about mainly on my research experience in underground. Okay, so this is the outline of this talk. First, I have a brief introduction. Then, I would like to move on to studying the universe with neutrinos, supernova neutrinos, neutrino oscillations, and mystery of the matter in the universe. Then, I'd like to move on to the studying the universe with the gravitational waves. And in particular, I want to talk about a facility in underground. And I'll summarize this talk. Okay, let's begin. Well, the story began slightly more than 100 years ago. In 1912, Victor Hess measured the intensity of radiation at the balloon altitude. Well, before the flight, people realized that on the ground, there were radioactivities, and people thought this must be coming from the ground. And if the idea was correct, then if you are away from the ground in the upper atmosphere, the radiation level should decrease. However, he discovered that the intensity increased with altitude. And this was the discovery of cosmic radiation, or I would say discovery of cosmic rays. Well, this was, in fact, I think, a great discovery because we understood that there are phenomena in the universe that cannot be observed with optical telescopes. So since then, over the last 100 years, cosmic rays have been studied very intensively. Now, cosmic rays are very exciting fields. Cosmic rays, including high-energy gamma rays, neutrinos, and gravitational waves, are telling us the secrets of the universe. Okay, let me introduce the modern observations of cosmic rays. Well, there are many satellites that try to observe gamma rays or cosmic rays in the space. In addition, on the ground, there are various observatories that try to observe gamma rays, cosmic rays, or even gravitational waves. And now, if you go underground or underwater or under the ice, there are observatories to observe neutrinos, dark matters, and gravitational waves. So, in fact, this slide will tell you how actively we have been studying cosmic ray-related phenomena. And in fact, since there are too many scientific topics in cosmic rays or astroparticle physics, I would like to concentrate on neutrinos and gravitational wave studies. Okay, now, so the first topic is about neutrinos. Well, I understand today there are, general public, therefore, I thought I need some introduction of neutrinos. So therefore, I prepared this slide. So this slide summarizes what are neutrinos. Well, neutrinos are fundamental particles like electrons and quarks. Well, still, it's unclear for you what are neutrinos. Then I'd like to add that neutrinos are something like electrons, but without electric charge. So, in fact, this has a very profound impact on the behavior of neutrinos, because neutrinos do not feel electromagnetic forces. Therefore, neutrinos can easily pass through everything, pass through the Earth or even the sun. And, well, however, on the other hand, neutrinos sometimes interact with matter. Therefore, it is possible for us to study neutrinos. And therefore, if we can study neutrinos, or if we can observe neutrinos, neutrinos can bring information of the fundamental processes at the center of the stars. And also, I want to say that neutrinos have three types, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to say that neutrinos have been assumed to have no mass. Now, let me very briefly talk about how we observe neutrinos. First of all, we can never observe neutrinos themselves. However, as I mentioned briefly, very rarely neutrinos may interact with the nucleus, with matter. For example, a neutrino may interact with the nucleus, and in this case, a charged particle typically appeared. And in fact, we have various methods to observe these charged particles. For example, if this charged particle propagates in water, then this particle emits photons or light. Therefore, if we have photodetector in our detector system, then we can observe this light or photons, and this way we know that a neutrino interacted at that time and charged particle propagated. So this way we can observe neutrinos. Now, you may wonder, well, at the beginning, I mentioned the title, and it said underground. Then you may wonder why we go underground. Well, in fact, cosmic rays are serious background to the studies of neutrinos. And well, here in this slide, in the right side, the image of the cosmic rays entering into the atmosphere is shown. In the atmosphere, one single cosmic ray particle produces many other particles. And these particles are a serious background to the studies of neutrinos. And we can only avoid them by going deep underground. In fact, deeper is better. Therefore, many neutrino experiments are located deep underground. Okay, now I want to talk about supernova neutrinos. The experiment I'm going to talk from now is the Kamiokande experiment. It was a very large water detector. It contained 3,000 tons of water. And it had about 16-meter diameter and 16-meter high. And in fact, well, here I show a photo of the Kamiokande experiment. And this experiment was constructed deep underground. And actually, this experiment was constructed to observe proton decays. Well, about 50 years ago, there was a new theory at that time, which was called grand unified theories. And these theories predicted that protons should have a finite lifetime of about 10 to 30 years. And in fact, physicists around that time were excited with this prediction, and therefore several proton decay experiments were constructed, and one of them was the Kamiokande experiment. Well, this experiment started in 1983, but we didn't observe proton decays. However, we found that the photomultiplier tube photodetector, which is shown in this photo, has a very good sensitivity. Therefore, Professor Koshiba, who was my thesis advisor, proposed to observe boron-8 solar neutrinos, neutrinos from the sun. Well, it was not easy, because originally this experiment was designed to observe proton decays, but the solar neutrino signal is very weak. about 1% of the proton decay signal, very weak. Anyway, he thought with this photomultiplier tube or photodetector, it must be possible to observe solar neutrinos. Therefore, we decided to improve the Kamiokande detector to observe solar neutrinos. Now, you may wonder why you want to observe solar neutrinos. First of all, the sun generates energy by nuclear fusion processes. We believe so. And neutrinos are created by these processes. Therefore, the observation of solar neutrinos is very important to understand the energy generation mechanism of the sun. And in fact, already in the 1960s, the Homestake experiment observed solar neutrinos for the first time. However, there was a problem. The observed event rate was only about 1/3 of the prediction. People didn't understood what happened. Anyway, this problem was called missing solar neutrino problem. Anyway, so in Kamiokande, we wanted to confirm, well, first of all, we wanted to observe solar neutrinos, and we wanted to confirm if the missing solar neutrino problem is a real problem by an independent experiment. So, well, in 1984 to 86, we tried to modify, improve the Kamiokande detector, and we were ready to observe solar neutrinos at the beginning of 1987. Then, unexpected event happened. This is a photo of the Large Magellanic Cloud in February 1987. Well, there are two photos, before and after. And in a photo after, you see a very bright star. And in fact, this was the supernova that happened in February 1987. As I mentioned, from the beginning of this year, Kamiokande was restarted the experiment with the sensitivity to low energy neutrinos. In fact, around that time, there were 3 neutrino detectors operated, including Kamiokande. Other ones are IMB and Baksan experiments. So, all these 3 experiments looked at their data and then found that these 3 experiments observed neutrinos from supernova. Here in this graph, I show a summary of the observation of supernova neutrinos by 3 detectors. Blue data from Kamiokande, green are from IMB experiment, and red are Baksan experiment. So, in total, 24 neutrino events were observed. There were only 24, but these 24 neutrino events were enough to understand the basic mechanism of the supernova explosion. Namely, we understand when a massive star finished its life, the star collapses, a shock wave is generated, and the outside of the star explodes. So well, this was really a great observation, and indeed, my thesis advisor, Professor Koshiba, received Nobel Prize in Physics in 2002 for this observation. By the way, well, I said, we have been trying to improve the detector essentially for 3 years, and finally, in January '87, Kamio Kande began to observe low energy neutrinos, and then in February, Kamio Kande observed these supernova neutrinos. By the way, in a month, he was expected to retire. So many people said to him, he was very lucky. Then he said, many people said, I'm fortunate. However, at that time, neutrinos came to everywhere on the Earth. Only people who prepared for them were able to observe them. Well, I think this is a very important word, at least for scientists. We should not forget about this, his word. Also, I'd like to remind you, Kamio Kande started as a proton decay experiment. Then, due to the good performance of the newly developed world's largest 50-centimeter photodetector, Professor Koshiba proposed to observe solar neutrinos in Kamio Kande. And finally, Kamio Kande observed supernova neutrinos. So clearly, this story tells us that scientific development may not be linear. Okay, now I'd like to move on to the other experiment, that is Super Kamio Kande. Well, Super Kamio Kande is in fact a larger version of the original Kamio Kande experiment. It is a 50,000-ton water detector. It has about 40 meters in diameter and 40 meters high. And here, I show a photo of the Super Kamio Kande inside. And well, if you look at the photo carefully, you see there are 3 people on a plastic boat. So then you may realize how big the detector is. Indeed, it's big. And well, in fact, in order to operate and analyze data from Super Kamio Kande, we need many scientists. We need many brains. So it is an international collaboration. We have about 230 collaborators from 11 countries. Now, I want to talk about the supernova neutrinos. Well, in fact, the Super Kamio Kande experiment started taking data in 1996, and since then, we have been trying to observe supernova neutrinos. Unfortunately, there have, in the last 30 years, there have been no supernova neutrinos, well, no supernova explosion in the Milky Way galaxy. It's unfortunate, but of course, on the other hand, the expected supernova rate is about, say, only 1, or even if you are optimistic, only 2 per century. So, well, maybe it's natural that we have not observed any supernova neutrinos. But now, Well, in the history of the universe, this is the cartoon of a universe. The horizontal axis is time, and the vertical axis is the size of the universe. The supernova explosions have been occurring somewhere in the universe. And in these supernova explosions, neutrinos should have been produced, and these neutrinos should be traveling in the universe. Therefore, we have been thinking that we should observe neutrinos produced in the past universe by supernova explosions. Well, okay, that was an idea. However, people realized that the original configuration of Super Kamiokande was slightly, say, not good enough to really observe supernova neutrinos produced in the past universe. Therefore, we thought we have to improve the detector. Well, that is the improvement could be too much technical things. But anyway, in the last almost 20 years, Super Kamiokande collaboration have been working hard to improve the Super Kamiokande sensitivity. And finally, we largely modified the detector. And in fact, this photo shows the new water purification system. And in fact, now in the Super Kamiokande detector, water, we put gadolinium in the detector water. So this is the new water system that purifies the Super Kamiokande water with the gadolinium inside the water. And with this improvement work, Super Kamiokande indeed improved the sensitivity to past supernova neutrinos. Unfortunately, today, I do not have definite data to show, but the early data are very interesting. So please stay tuned for new data from Super Kamiokande. Okay, from now on, I want to switch to other topic, neutrino oscillations. Well, first of all, let me tell you what are neutrino oscillations. Neutrino oscillations were theoretically predicted more than 60 years ago. Well, these people, Maki, Nakagawa, Sakata, and Pontecorvo, these people predicted if neutrinos have mass, neutrinos change their type from one type to the other. For example, a mu neutrino could oscillate to tau neutrinos. Here in this graph, we assume that a mu neutrino is created at point 0 and propagate to the right. Then, at some point, the probability that a mu neutrino is remaining as mu neutrinos go down. And at that time, tau neutrino is appearing. But if this neutrino continues to propagate, then the probability that mu neutrino is remaining as mu neutrino come back to unity. Then at that time, tau neutrino is completely disappearing. So this continues. So this way, we say neutrino oscillations. And this means if we observe neutrino oscillations, we prove that neutrinos have small mass. And for this, we studied neutrinos produced in the atmosphere of the Earth. Well, here I show how these neutrinos are created. Well, cosmic ray particles come into the atmosphere of the Earth from somewhere in the universe. They interact with air nucleus. Then typically, a particle called pion is produced. But pion is an unstable particle and therefore decay to other particles. And during this decay, neutrinos are created. And sometimes, one of the neutrinos may interact in the super Kamiokande detector. And the neutrino event look like this. So, from the beginning of the experiment, we have been observing these neutrinos. In fact, early atmospheric neutrino data from the Kamiokande and IMB experiment. IMB experiment was an experiment in the United States. These experiments showed missing muon neutrinos in the atmospheric neutrinos. Unfortunately, Kamiokande and IMB were unable to understand why they observed missing muon neutrinos in atmospheric neutrinos. And one of the possible answers to this problem was neutrino oscillations. But of course, we needed a very clear data that demonstrate neutrino oscillations. And therefore, in super Kamiokande, we thought this way. Well, as I said, neutrinos are created in the atmosphere, and therefore some of the neutrinos are created above the super Kamiokande detector, maybe 10 to 20 kilometers above the detector, and these neutrinos come to the detector after traveling a short distance of 10 to 20 kilometers. So maybe these neutrinos do not have enough time to oscillate. On the other hand, neutrinos are also created in the other side of the Earth. And these neutrinos come to the detector after traveling a very long distance inside the Earth. Therefore, these neutrinos created in the other side of the Earth may have enough time to change their type. So, if we think this way, we thought we should observe the up versus down asymmetry of the atmospheric muon neutrinos. And if we observe this kind of asymmetry, we thought that this could be the evidence for neutrino oscillations. So from the beginning of the experiment, we tried to observe this kind of asymmetry. And indeed, in 2 years, we are able to show the first significant result from super Kamiokande. And here, I show a copy of the slide we presented at the Neutrino 1998. By the way, in the 20th century, we didn't have PowerPoint. So, well, at that time, we used an old technology. We copied our data to a plastic film and wrote down various comments and showed to the audience of the conference. Anyway, there's a reason that I showed this slide. Because this was really important. Well, please look at the lower panel. That shows the muon neutrino data. And cosine theta means neutrino arrival direction, and horizontal axis. And 1 means downgoing neutrinos, and -1 means upward-going neutrinos. They came from the other side of the Earth. And the black circles with error bars show the data, and the hatched histogram show the prediction without neutrino oscillations. Then you see, for downgoing neutrinos, the data and the prediction agreed very well. On the other hand, for upward-going neutrinos, the data is only about 1/2 of the prediction. So this can be very well understood if we assume neutrino oscillations. Namely, neutrinos produced in the other side of the Earth oscillate while propagating in the Earth. So this way, we were able to convince the world neutrino community that neutrinos oscillate. Namely, neutrinos have very small mass. Now, before moving on to the other topic, I'd like to tell you a little bit about the story. Already around 1986 in Kamiokande, we found that the observed number of atmospheric muon neutrinos was significantly fewer than expected. Since then, we have studied atmospheric neutrinos to understand why the observed number was much fewer than expected. In fact, in the 80s and 90s, many researchers were skeptical of the Kamiokande results on atmospheric neutrinos. But I was unable to forget about the problem. Well, actually, to be honest, I thought that the missing atmospheric muon neutrinos might be due to our problem. Our mistake somewhere. Or, if this is not the case, something fundamentally important. Anyway, it took slightly more than 10 years to conclude that the missing atmospheric muon neutrinos were due to neutrino oscillations. So slightly more than 10 years we took. We think that we are very fortunate. We discovered neutrino oscillations simply by trying to understand why we did not observe as many neutrinos as predicted. Anyway, please remember, in scientific achievements, it takes time. In this case, we were able to understand the problem in about 10 years, but I think we were fortunate. Because from now on, I want to switch to solar neutrinos. And in fact, solar neutrino problem was understood to be due to neutrino oscillations. However, the problem was found already in 1960s, and then finally in this century, we understood that was due to neutrino oscillations. So it took more than 30 years. So I think we need to understand the time scale for achieving significant scientific results. Okay, now I want to move on to solar neutrino oscillations. In the 20th century, several experiments observed solar neutrinos. Here, I listed the solar neutrino experiments that successfully observed solar neutrinos. Homestake, Kamiokande, Sage, and Galaxy GNO. And these solar neutrino experiments confirm the missing solar neutrinos. However, during the 20th century, it was not possible to understand the reason for the missing neutrinos. Then we needed a newer generation of solar neutrino experiment. And in fact, there was already an idea in 1985. The person who had this idea was Herb Chen. He thought that we should observe the total neutrino flux and the electron neutrino flux separately. And if the missing solar neutrino problem was due to neutrino oscillations, electron neutrino flux should be much lower than the total neutrino flux. That was the idea. And for this, he proposed a large heavy water detector. Heavy water means, well, in the normal water, it's H2O, 2 hydrogen and 1 oxygen. But in heavy water, there are 2 deuterons and 1 oxygen. And that was indeed the key. Anyway, based on this idea, the SNOW experiment was constructed. And indeed, it had 1,000 tons of D2O, heavy water. And, well, you can see a large flask structure. And in there, 1,000 tons of heavy water were contained. And since they used heavy water, it was possible to observe total neutrino flux and the electron neutrino flux separately. And this is the result from the SNOW experiment. In addition, I show the super Kamiokande solar neutrino data. So this SNOW experiment indeed observed the total neutrino flux and the electron neutrino flux. And indeed, they found that the electron neutrino flux was only about 1/3 of the total neutrino flux. Since the sun can only generate electron neutrinos, the SNOW data clearly indicated that the neutrinos from the sun had a nu plus nu tau component in addition to the nu e component. So that means the solar neutrino problem was due to neutrino oscillations. Okay, so this way, in early this century, we understood that missing solar neutrino problem was due to neutrino oscillations. And in fact, well, the whole neutrino community was really excited with the discovery of small neutrino mass or neutrino oscillations. And since then, there have been many exciting results in neutrino oscillations. And here, I show a list of the neutrino oscillation experiments. So you see, there are many neutrino experiments that contributed to our understanding of neutrino oscillations. And well, I would say that the whole community is coherently trying to understand neutrino oscillations better. And in a sense, global neutrino community is working together to understand neutrinos better. And in fact, well, we know that neutrino mass is very small, and we'd like to understand why neutrino mass is so small. But in addition, we think maybe neutrinos are key to understand a mystery of the matter in the universe. Well, this is a photo of the far universe. We see many galaxies. And, well, we know one thing. All these galaxies are made of matter. There's no antimatter galaxy. Well, maybe it's trivial, but on the other hand, we do not understand why the present-day universe is simply dominated by matter, because, well, about 13.8 billion years ago, our universe was born, and at the beginning of the universe was extremely hot. And in the extremely hot universe, always particles and antiparticles are created simultaneously. Therefore, at the beginning of the universe, we simply expect that the number of matter particles and antimatter particles should have been equal. Then, universe expands and cools down. Then it is no more possible to create particles and antiparticles. Instead, if a particle and antiparticle meet, annihilate, disappear. So, we naively expect that there should be no matter, no antimatter remaining in the present-day universe. But of course, experimental observation is simply matter-dominated. Why? Again, we do not know. But there's an interesting idea that neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So, this means if we understand neutrinos better, we maybe understand the big mystery of the matter in the universe. So, well, in fact, neutrino physicists were excited with this idea, and we'd like to know if neutrinos are related to the origin of the matter in the universe. And, well, of course, that was a great idea, but, well, this was a theoretical idea. Maybe this is correct, but we have to test with the experiments. And so, to do so, first of all, we'd like to observe if neutrino oscillations of neutrinos and those of antineutrinos are different. Well, it's a little bit complicated. Anyway, well, the expected difference is small. Therefore, the present generation of neutrino experiments are not powerful enough, and we need the next generation neutrino experiments. And indeed, there are two very large neutrino experiments are under construction, one in United States and one in Japan. And since I'm from Japan, let me talk about the Japanese project. It is called Hyper-Kamiokande. And, well, we try to observe more neutrino events than Super Kamiokande. And for this, we need even larger detector than Super Kamiokande. So at present, in Japan, people are constructing a larger detector which has about 70 meters in diameter and 70 meters high. Well, here I show a photo of the Hyper Kamiokande construction. At present, excavation was completed and people are constructing the water tank. And you see at the bottom, there are various equipment. In fact, they are very large machines. So indeed, it's really a big experiment. And in fact, it is an international collaboration, about 650 people from 23 countries and regions. And the experiment will start in 2028. So we hope to see a new exciting result from this facility in the near future, in a few years. Now, I'd like to completely switch to a new study, studying the universe with gravitational waves. So, since the topic is completely different, I want to have a brief introduction. Well, gravitational waves were predicted by Albert Einstein in 1916 based on his theory of general relativity. Well, here I'd like to show you one example of the gravitational wave generation. This is, in fact, a video. Let me show. Well, here you see two black dots. They are two black holes. They are orbiting each other. Then, well, from this system, gravitational waves are generated and propagate to the outer space. And therefore, the black hole binary system loses its energy. Therefore, these two black holes come closer, therefore orbiting faster and faster. Then come closer and closer, and here they artificially slow down the video. And then finally, two black holes merge, and a heavier black hole was created. And if you look outside space, you find that gravitational waves propagate to the outer space. So this is the image of the gravitational wave. So we'd like to observe these gravitational waves, and we'd like to observe the merger of two black holes. Then the question is how we should observe them. And in fact, if the gravitational wave come to the Earth, then the expected effect is the, I would say, length change. The length between two objects may change due to gravitational waves. And for this, we use laser interferometer technology. Okay, again, this is a video. Let me show. Okay, so this is the laser interferometer, and laser is emitted, and here the beam is split into two and reflected back to the beam splitter, and these two beams meet, and there is an interference. And typically, the interference light is tuned to be minimum. But in some reason, the distance between the beam splitter and the far mirror changes. then the interference light intensity changes. So this way, we expect to observe gravitational waves. And indeed, on September 14th, 2015, the LIGO interferometers in the United States observed a signal with the two laser interferometers. Well, here in this slide, in the upper left, I copied the data on that day. There are two graphs. One is shown by blue and another by red. And you find these two data agreed quite well. And in fact, these two data came from two independent laser interferometers in the United States. So from this data, the LIGO scientific collaboration concluded that this was the first observation of gravitational waves. And the data, this data, told us that two black holes of 36 solar mass and 29 solar mass merged at a distance of 1.3 billion light years. We thought this was indeed a great discovery. And indeed, well, the announcement of the discovery was made in 2016. Then in 2017, the Nobel Prize in Physics was awarded to these three people. So indeed, we think this was a great discovery. Well, that was slightly more than 10 years ago. And since then, LIGO improved the detector system. In addition, in Europe, Virgo was also joined the observation. And this is a summary of LIGO and Virgo observation of gravitational waves until January 16, 2024. Well, here, the horizontal axis has essentially no meaning. Just please see the vertical axis. The vertical axis shows the mass of stars in solar mass unit. And blue circles show black holes. And orange circles show neutron stars. And so far, 218 gravitational wave events were observed, and most of them are binary black hole mergers. In addition, there are several binary neutron star and neutron star black hole merger events. So clearly, now we enter into a new astronomy, gravitational wave astronomy, with these many events. You may wonder, what kind of science do we expect from these observations of gravitational waves? And in fact, well, we think it's very important to have gravitational wave data. For example, the merger of binary neutron stars, we think it's very important because we think that the merger of binary neutron stars are directly related to the origin of the heavy metals in the universe. Well, until recently, we didn't have any observational evidence for the generation of gold, for example. We had no idea where in the universe the gold was generated. But with the first observation of the merger of binary neutron stars, we understood that maybe this is the place to generate gold we see on the Earth. Furthermore, as I mentioned, so far we already observed many black hole mergers. And in fact, the data are quite interesting. LIGO and Virgo already observed rather heavy black hole mergers, heavier than we naively expect, that these black holes are created by normal stars. So we have to understand what are these rather heavy black holes. So there are indeed many science with gravitational waves. And therefore, we are now trying to contribute to this exciting new scientific field by constructing a new facility in underground. The new facility is called Kagura, and this is again an international collaboration. And you may wonder, well, in fact, LIGO and Virgo are located on the surface, but we decided to construct the Kagura laser interferometer in underground, deep underground. Why underground? In fact, the seismic activity is much smaller in underground. And therefore, it is much easier to control the detector system and to reduce the seismic noises. In fact, seismic noises are a serious background to the gravitational wave detectors. So we decided to go underground. Indeed, the Kagura project was approved by the Japanese government in 2010. And for about 10 years, we simply worked hard to construct the Kagura detector in underground. So we constructed the 3-kilometer vacuum, well, there are two 3-kilometer vacuum tubes, and this photo shows one of them. And we had the installation work of these mirrors and so on. And in particular, I want to mention, we decided to use sapphire for the main mirror of the Kagura detector system. We use 23-kilogram man-made sapphire. And in fact, we cooled down this mirror to about 20 Kelvin. Well, in fact, there's a reason that we use sapphire and cool down the mirror. Well, in fact, even today, it's not easy to observe gravitational waves. Well, you have to observe a very small length change. Well, we expect about 10 to minus 16 centimeter length change in 3 kilometers. And therefore, even a thermal effect of the mirror is a problem. Therefore, we decided to cool down the main mirrors to 20 Kelvin to reduce the thermal effect, thermal noises. Anyway, after 10 years of the construction, we began the operation, well, not really observation, but began the operation of the interferometer. And at the same time, we decided to work together with LIGO in the United States and Virgo in Europe. Of course, there is a reason to work together. Well, it's very important to tell the astronomers from where the gravitational wave came. And therefore, we have to decide precisely from where the gravitational wave comes. But in order to do so, we need at least 3 detectors which are located far apart from each other. Therefore, we thought it's very important that Kagura, located in East Asia, join the observation. So the gravitational wave detectors, LIGO, Virgo, and Kagura, work together. Namely, we are observing gravitational waves simultaneously, sharing the data and analyzing the data as a team. Of course, Kagura joined this observation later. And in fact, Kagura only rejoined the observation on June 11th last year. But still, our sensitivity is not enough. Therefore, at present, practically, we are still unable to contribute to the gravitational wave observation. But we hope that we can improve the sensitivity significantly in the next 3 years or so. And finally, I'd like to mention one thing. Well, this is a bit too detailed, but, well, we have been thinking what our contribution to the global network of the gravitational wave observation. And we think that one of the important scientific topics is the observation of the mergers of binary neutron stars. This is the computer simulation of the merger of the binary neutron stars. And, well, in this process, strong gravitational waves are expected to be emitted before and after the merger. and in fact, based on the scientific importance and the feature of the Kagura interferometer, as I said, we decided to use sapphire mirror. This is the key. And therefore, Kagura decided to improve the sensitivity in the high frequency range, kilohertz range, to be able to observe the gravitational wave signal just before the merger and after the merger. So this way, Kagura would like to make a unique contribution to the international LIGO-Virgo-Kagura network in the 2030s. Okay, let me summarize my talk. As I discussed, underground experiments are very important for unveiling the secrets of the universe. In particular, neutrinos and gravitational waves are exciting scientific fields. And I believe many more fundamental discoveries will be ahead of us. And finally, well, this has nothing to do with the present talk, but, well, I want to mention that even amidst the outrageous actions of politicians lacking humanity, I believe that scientists should work together to advance science and show what humanity should be. Okay, that's all from me. Thank you very much.
Professor, thank you very much for your inspiring lecture. We would like to ask you for question and answer session. So,
thank you. Professor Kajita, at the beginning of the lecture you mentioned that neutrinos were thought to be massless, and this made me wonder, how is that possible that there exist two separate entities entirely like light and something else that can have no mass, but be counted as something else entirely? And also another part of my question is about black holes. Like, we know that they can be pulled, like black holes can pull the light inside, can be affected by them, despite having no mass. But there exist other things that have mass, like Hawking radiation, that can be pulled towards the black hole. And you mentioned that neutrinos despite having mass, can go through the sun. And my question is, can they also go through the black holes? Maybe one more thing I want to, to be precise.
Sorry.
Okay.
I already forget first question. Second question before forgetting. Well, certainly. Even if neutrinos can come from the center of the sun, neutrinos cannot come from the black hole. Well, independent of what are they cannot escape from the black hole.
Okay, and that my first part of the question about like properties of massless particles. Like we know that light can have different properties depending on its wavelength, but like what makes it different from another thing that would have no mass? And are there examples other than light that have no mass?
I'm afraid in fact, I do not understand your question very well.
Can I try to be specified once more? That we know that light has no mass, and we also thought that neutrinos had no mass. But what made us separate light from neutrinos? Like, how do we know that it's not just light of different wavelengths, for example?
Thank you. In fact, well, okay, good question. Neutrinos and light are fundamentally different. For example, neutrino spin is 1/2, photon spin is 1.
Okay, thank you very much.
Okay, firstly, I wanted to thank you for a really great lecture. And I have one or maybe two questions. So with Super Kamikande and all the other detectors, you're looking for neutrinos coming from space, from the cosmos. But I know in the world, and Japan also has a lot of nuclear reactors, and obviously they produce a lot of neutrinos as well. So I wanted to know, how do you account for those neutrinos? Like, how do you subtract them from the ones coming from space?
Thank you. First of all, about the neutrinos created in the nuclear power stations. Well, okay, now essentially I left the Super Kamikande collaboration. Therefore, at present, I do not know the details of the collaboration. But, well, I mentioned that Super Kamikande have improved their detector system by putting gadolinium into the Super Kamikande water. And with this improvement, now it is possible to enhance the sensitivity to anti-neutrinos, anti-electron neutrinos. And, well, in the original configuration of Super Kamikande, it was not possible to observe reactor neutrinos. There are so many backgrounds. But with this improvement, in principle, I think Super Kamikande can detect reactor neutrinos. But I don't know the details.
Okay, thank you. So my second question would be if the Fukushima disaster impacted that in any way, your research and all the other detectors?
Fukushima disaster, well, okay. In a sense, it affected some experiments. Well, in fact, in Kamioka, in the same mine, there is another experiment called Kamran. This experiment was designed to study neutrinos from nuclear power stations. And in fact, this experiment had a really significant contribution to the understanding of the solar neutrino problem. But, of course, after Fukushima, essentially all the nuclear power stations stopped the operation. And therefore, since then, this Kamran experiment cannot continue the reactor oscillation experiment. On the other hand, the Cameron experiment was the first that observed neutrinos produced in the Earth, geoneutrinos. However, before 2011, they had a significant background. Background was the nuclear reactor neutrinos. After 2011, these nuclear reactor neutrinos essentially disappeared. Therefore, they have a cleaner geoneutrino signal.
Thank you very much.
Professor, thank you very much for the great lecture. I think it's an amazing capability to talk about such a difficult things in the way that also not academics can understand. So thank you very much for this. Partially already answered the question of the colleague, previous one. I wanted to check, looking at the neutrinos which you discover, would you expect there will be more to come? And the second part would be...
Sorry, once again.
If it will be more types to come, do you believe there will be more types of neutrinos to come? Looking at the continuation of the research.
Mm-hmm.
And this is also about neutrinos, practical usage in the modern world.
Practical use?
Yes.
Okay, thank you. Well, in fact, unfortunately, other source of neutrinos, we do not have good idea. Well, now the new experiment, Hyperkamiokande, which is under construction, is going to observe neutrinos produced by accelerator, which is located 300 kilometers away from Hyperkamiokande. So this experiment is going to have a dedicated neutrino oscillation experiment with the controlled neutrino beam. So maybe at least, well, okay. So certainly this is one way. And in addition, I want to say this is nothing to do with the experiments in Kamioka, but, well, certainly neutrinos are very important to understand how the cosmic rays are created, generated, accelerated in the universe. And, for the last 100 years, people try to understand from where the cosmic rays particles come. However, there is a fundamental problem. Cosmic rays are charged particles, and in the universe, there are magnetic fields. Therefore, cosmic rays are bent by the magnetic field. Therefore, we were unable to understand from where these particles come. But now, in the South Pole, at least in the South Pole, there's a large neutrino facility to be able to observe these very high energy neutrinos. And in fact, the data already tell us from, at least part of the cosmic ray, from where these cosmic rays come. And in addition, now in Europe, in the Mediterranean Sea, a new facility is under construction. So with these facilities, I hope in the near future, we understand much better about the origin of the cosmic rays. Another practical use of neutrinos. No idea.
Okay, so I have a question a bit similar to the one earlier. You mentioned in the beginning of the lecture that neutrino detectors are often built underground so as the results are not disturbed by other types of cosmic radiation, but I presume that sometimes some non-neutrino particle does show up in for example, in this great water tank. So how do you account for those in experiments? Is it just a matter of tuning the detectors, or is there something else that has to be done?
Oh, well, first of all, sorry. It took me so many time to find you. Well, could you repeat your question? Key part, only key part.
How do you account for non-neutrino particles that show up in neutrino detectors?
Thank you. Okay, thank you. Yeah, in fact, as I said, cosmic rays are serious background. And, well, even, say, 1,000 meters deep underground, still, majority of the events are cosmic rays. Therefore, we need a very efficient way to separate neutrino signal from background cosmic rays. And for this, for example, in Super Kamiokande, in fact, we have 2 layers. One is the inner volume. That volume is used for detecting neutrinos. In addition, we have the outer layer. And, well, typically, neutrino signal is, well, neutrino interactions in the inner volume and propagate and stop in the inner volume. Therefore, the signal is only detected in the inner volume. However, cosmic ray particles come from above and enter into the detector system. Therefore, typically, these cosmic rays have a signal in the outer layer of the detector. And therefore, we are able to separate the neutrino signal from the cosmic ray background.
Hello, Professor. Thank you for the lecture. One question about KAGRA. If it's going online in the 30s, it will help with triangulation, of course, but will it also have higher sensitivity that will allow to detect new events as well that are not detectable by LIGO and Virgo?
Okay, thank you for this question. Well, okay, my answer is this way. Well, okay, thank you for this question. In fact, well, we are trying to improve the sensitivity, but at the same time, LIGO and Virgo are also trying to improve the sensitivity. So, what we decided was, we tried to be sensitive, most sensitive in a slightly different frequency range. And, well, we would like to be most sensitive in the kilohertz range, so that we are most sensitive to these neutron star merger events. This is our strategy. And in fact, in order to achieve very high sensitivity in kilohertz range, definitely a very important element is the sapphire mirror, cryogenic sapphire mirror. Based on this technology, we were able to decide our science target to the kilohertz range.
Hi, thanks a lot for your presentation. And I wanted to ask you, how do you determine which supernova a specific neutrino comes from? Like, you had a slide about our universe, and that during its, when we had our universe, there were some supernova and they were exploding, and after they explode, there were neutrinos arrive. Yeah, and how do you determine which supernova a specific neutrino comes from?
Thank you. We are unable to tell from which supernova this neutrino come. No way.
Okay. And second question: do mathematicians need to study physics?
Thank you for this question. Well, it will be, of course, very nice if mathematicians study physics, and they may contribute to physics in a significantly different way, and that will be a fantastic contribution.
Thank you, Professor Kajita, for an interesting lecture. You mentioned that in Super Kamiokande, dissolving the gadolinium in water improved the results. And I am curious as to why does the gadolinium improve the results?
Thank you for this question. Yes, well, okay. in order to observe supernova neutrinos, we have to know which type of neutrino we are going to measure. And we are going to measure anti-electron neutrinos. And all the other neutrino interactions, mu neutrino interactions, electron neutrino interactions, tau neutrino interactions, well, tau neutrino do not interact. Anyway, other neutrino interactions are background. Now, anti-electron neutrino interactions on protons produce positron plus neutron. And typically, water Cherenkov experiment can only measure electrons, positron signal. Now, we put gadolinium into the super Kamiokande water, and gadolinium is known to have a very high cross-section of absorbing neutrons, thermal neutrons, and therefore, in the super Kamiokande at present, the neutrons are captured by gadolinium. Then gadolinium emits total of about 8 MeV gamma rays, and these become a signal for the super Kamiokande detector. So therefore, first positron signal, and several tens of microseconds later, neutron capture signal. By observing this kind of coincidence, we can separate the signal from the other neutrino background. And this way, we can significantly enhance the sensitivity to fast supernova neutrino events.
Okay, thank you very much.
Yeah, we have the last question here.
Thank you, Professor, for this amazing lecture. I just wanted to ask 2 questions. First of all, is there any way to theoretically store neutrinos to generate energy? And second of all,
sorry, neutrinos to generate energy.
I think they have some kind of energy output, so they could be stored somehow.
I'm sorry, I don't understand your question.
Sorry, I just asked the wrong question. Is there any way for neutrinos to not penetrate something? So is there some object that they can pass through?
The object that neutrinos cannot easily pass through?
Yes.
In fact, it's a good question. Well, in this talk, I didn't mention much about the neutron stars. Well, in fact, when supernova explode, at the center of the supernova explosion, there's a newly born neutron star. And in fact, neutron star has an extremely high density. And in that extremely high density material, neutrinos cannot easily come out. Well, in fact, neutron star has about 25 kilometers in diameter, but for neutrinos come out from this neutron star, it takes about 10 seconds. So neutrinos interact many times before coming out.
And my second question is, how are neutrinos affected by gravity?
Oh, same way other particles.
Okay.
Yeah.
Thank you.
Thank you very much. Dear Professor, thank you very much for this beautiful, inspiring lecture.
Thank you.
And also thank you very much for your presence here during our seminaries.